Okay, so in such a situation in which the temperature is constant, the pressure is constant, one has to minimize the Gibbs potential. And we will see that this is the case, typical case, in which we have first order phase transition that we will analyze maybe today, in which typically the conditions are such that the pressure and the temperature is fixed, and one has to minimize the Gibbs potential. We will see also later that this minimization basically can describe the tendency of the system to go towards chemical equilibrium in particular. Okay, we will see later. So once we have these three versions of the second principle of thermodynamics, one can work out some example. We have done the example of maximization of the entropy, which was realized by having two systems with different temperature. And we say that once the temperature of the two systems is equal, then we have reached the maximum of entropy. Then we had, we will see later on an example with the Gibbs potential. Now let me do some more work, some exercise basically, a couple of exercises that I will just sketch with the which makes use of the Helmholtz free energy. So we have a system like that. So these are our exercises. We have the usual box here with T constant. And now here we have a piston which is connected to a spring to this part of the wall. And when here there is this vacuum, the distance between the piston and this part of the wall is x0. So here vacuum with 2u. And once, so the system is kept at T constant, of course the volume, the total volume of the system does not change, in the sense that the piston can just move, but this part and this part, the total will conserve the volume, so therefore the total volume is constant. And the question is, what happens when I introduce in here in the left part and 1 mole of ideal gas. Opla. Now, once we introduce here 1 mole of ideal gas, the question is which is the position of the piston. Once we know that the surface of the system, of the piston is sigma. Sigma is the surface of the piston. Okay. So the situation is the following. At rest, without gas here, the spring is at a distance x0 with respect to this side of the wall. Now we put n equal 1 mole of ideal gas, everything is kept at T constant, and we ask ourselves which is the position of the piston. This is a classical problem of thermodynamics, no? Now the thing is that in this kind of problem, somehow thermodynamics is mixed with mechanics, in the sense that, but we can see how to do it. There is of course, a mechanical energy related to the potential energy of the spring, and there is the free energy of the gas. Indeed, since the T is constant and the total volume is constant, one has to minimize A tot. It's a total Helmholtz free energy. Okay, this is the second principle of thermodynamics that tells me what the final evolution, the final state of the system is. So let's try to do it. So maybe I can erase this, which you have it now. And let us first remind us which are the relation between the variation of the Helmholtz free energy and other thermodynamical quantities, which are in this case minus the pressure times dV minus entropy times dt. Okay. Now, what happens here is that we will have a contribution of Helmholtz free energy plus, which is related to the gas, plus the potential energy associated with the spring. And in particular, if we compress the spring, since this was going to happen, no? Intuitively, once we introduce a gas, we will move the piston towards to the right direction. No? So we will have a contribution to the energy, which is the standard potential energy of the spring, which is x minus x0, and k is the constant characterizing the spring. Okay. And what we have to do now is to impose, so this, if you want, is the total free energy, Helmholtz free energy. We have to impose the dA equal to 0, which means dA associated with the gas plus, I have to differentiate this term here, which means k times x minus x0, and I have to impose that this is equal to 0 by using the second principle of thermodynamics. Okay. Sorry, I have to differentiate, therefore there is a dx missing here, of course. And those are the two differentials. Now, from this equation, I get that dA gas divided by dx is equal to minus k x minus x0, minus k x minus x0. Now, let me divide by the surface of the piston, which was sigma, to the right and to the left. And now I have an equation which is the following, which is derivative of A gas divided by the volume. This is the variation of the volume, no, because it's dx times sigma, and so this is the variation of the volume of the gas. And now this is equal to minus k x minus x0 divided by sigma. Now we know that the derivative of A with respect to volume at fixed temperature, because we are working at fixed temperature, just the pressure, and therefore this will be minus the pressure of the gas. Okay, so from this equation, I can derive that minus P, where this is the pressure of the gas, is equal to minus K x minus x0 divided by sigma. Okay? Of course, now this equation, if you want, P here is a function itself of the position, because it will change depending on the position of the piston. But this equation, what is expressing is just the mechanical equilibrium, as we said last time. This is the indeed the pressure times sigma is just the force that the piston is acting on the gas, or the gas is doing is exerting on the piston, whereas this is the Hooke law, no, which is the force related to the deformation of the spring. So from the minimization of the total free energy, almost free energy, we get a relation of mechanical equilibrium, which was exactly the relation that we got last time. So then one has to solve at the end this equation. And now there is a little bit of algebra that I'm not going to solve. Just I can provide a solution if you want to try to do the calculations. So the equation that we have to solve of mechanical equilibrium is the following: is the pressure as a function of x is equal to k x minus x0 divided by sigma. Okay, this is the equation that we have to solve. Now one has to use the standard law. Now we have N1 mole, and therefore PV is equal to RT, where R is the constant of ideal gas, universal constant of ideal gas. And therefore here we can put, instead of P, we can put RT divided by V, and this must be equal to x minus x0 divided by sigma. What is V, the volume? The volume is just T is just sigma, which is the surface of the piston times x. Is equal to k x minus x0 divided by sigma. I can remove the sigma, and then I get an equation in which I have to find x. Blah blah blah. There is a little bit of algebra that I'm not going to compute, and at the end, if I have done my calculation correctly, we should get the following expression. So x should be equal to x0 divided by 2. Then I have 1 plus the square root of 1 plus 4 RT divided by k. Oh, sorry, x1 più 4 RT divided by k x0 squared. 0. Let me check if this is correct. 4 RT kappa. Okay, so this should be the final solution. One has to solve this equation, which is an algebraic equation, second order. Okay? Let's try to do another exercise, just sketch all this as another exercise, and then we move on. I guess when doing general physics, you have done this kind of exercises, no? So maybe I will not spend too much time on that. Okay. If it's okay for you. We are not going to repeat general physics, just to refresh a little bit. Okay, now we have another system. The system is the following. We have a box, again, in thermodynamics, this is the typical system. What we have, yes, what you still have is a piston here. Then we have two gas fixed volume, temperature, and pressure. Volume, temperature, and pressure, they are equal. Okay? And the total system is kept at T constant. Now, what we do is to rotate in presence of gravity this box, and the piston, it will have a weight in this case, and it will actually act with a pressure, or if you want, with a force, which is P0 times sigma. If you want, is the force from piston to what the second part, system 2, that then we call system 2. Let me make a draw in order to understand what's going on. So once we rotate and we are in presence of gravity, we will have the piston in a different position. Here it was just in the middle, whereas at the end we will have here the situation in which the pressure now is P1, the volume is V1, the temperature is constant, it's fixed to T. Here we will have pressure P2, V2, and T again. Now about this system, one can ask different questions. The first question is which is P1 and V1. Another question is which is the variation of the entropy of the two systems, and the total variation of the entropy, which is the variation of the entropy of the box plus the variation of the entropy of the source. Because when I say T constant, that means that the system is in contact with the thermal reservoir. And what we have else? I think that's are all the questions that we can try to answer. Now, one can do similarly to the previous case. One can do a kind of argument to establish. So okay, let's start from this. T is constant again, volume is constant again. We have to minimize the Helmholtz free energy, okay, as before. And to do that, we have to impose that the dA is equal to 0 in order to get the equilibrium, right? And dA, now what is dA? Is dA1 plus dA2, which are the variation of the Helmholtz free energy of system 1 and system 2. But I have to add another term here to this, say, energy balance, which is minus, and I will explain why it's like that, so minus P dV1. This is dA. I will explain in a moment what I have done there. Okay, so what is this? So this is the total variation of the total Helmholtz free energy. which is gets contribution of the variation of system 1, the variation of system 2, but I have to add another term, which is a mechanical term as before, which is provided by minus P0 dV1. What is this minus P0 dV1? Is what I'm losing of free energy from system 1, and which is going to system 2, because this system is forcing system 2 to be more compact. Therefore, I'm losing energy from system 1. That's why I have a minus there. So the volume V1 is increasing, and P0 is the pressure of the piston, and therefore I have a minus there. Okay. Now one can impose the following equation. Let me remove this plot here. Let me see what I have done. Come l'ho fatto questo qua? Okay, so now what I have to do, first of all, let us remind that dA divided by dV at fixed temperature is minus pressure. This is general, okay? Now, when I impose this dA equal to 0, basically what I have to do is a variation of A with respect to V1, for instance, which I take as an independent variable. I change V1 and I see what happens to A1, A2, and this term here. And then I impose that dA divided by dV1 at constant temperature is equal to 0. Okay? So when I do that, basically I have to derive this quantity with respect to V1, and I will get a minus pressure 1. So let's call it asterisk. So from asterisk, sorry, but to work with just this small blackboard, well, it's not whiteboard, it's not easy. And so when I do this, I get minus P1, because it's the variation of A1 with respect to V1, and then I get a minus, which is minus P1. Then let me see if I get the sign correct. I have a plus P2, and I will comment in a moment why I have plus P2. Then I have minus P0. Okay, this is easy because it is just minus P0, and then this must be equal to 0. Why I have minus plus P2, sorry? Because when I do the derivative of A2 with respect to V1, this is the derivative of A2 with respect to V2 times derivative of P2 with respect to V1. Now, the total volume, V, is equal to V1 plus V2, which was equal to 2 twice V. Okay, the initial volume of the two sides of the box was V, and therefore, since the total volume is fixed, then you see that V2 is minus, V2 is 2V, which is a constant, minus V1. Therefore, when I derive with respect to V2, I get the minus the pressure, minus P2, but then this derivative gets a minus, okay? Here. That's why I get a plus P2. Now, what is this equation? This equation is just an equation again of mechanical equilibrium, which can be written as follows. Vediamo come l'abbiamo scritta qua. Yeah, P1 plus P0 is equal to P2. Okay, P1 plus P0 is equal to P2. which is not very strange in the sense that P1 and P0 represent the total pressure acting on the system 2. No? There is a contribution from the pressure of the gas in the side 1 and a contribution of pressure given by the weight, if you want, of the piston. And at equilibrium, mechanical equilibrium, this must be P2. Okay? So this is one equation. The other equation that I have is the conservation of volume that I wrote before, which was V1 plus V2 is equal to 2V. Okay? And consider that everything is computed at T constant. So now I can just use the standard law, P1, V1 is equal to KB and T. I just write T because the temperature is the same, is always the same. P2, V2 is equal to KB and T gain. Now this is a system that can be solved. Is a gain once you must do some algebra. A little bit long, that's why I'm not going to repeat those calculations, but you can find from this equation, since pressure are a function of V1, now you have two equations and two volumes that must be computed. So that if you do the algebra, once you introduce this dimensionless quantity, which is P divided by P0, which is useful, you will get, so the solution, you will get that V1 is equal to V times 1 minus X plus X squared plus 1, and V2 is equal to V times 1 plus X minus X squared plus 1. Let me check if this is correct. Okay. So the two equations that one has to write are the equation of conservation of volume and the equation of mechanical equilibrium. You solve the system by using the ideal gas law, and then you find these two volumes, which are the volumes in the final state. Now the question one can ask are different. I will just catch the other questions and the other solutions, and then we move on. I think that one of the question was the following: find delta S1, delta S2, delta S, what I wrote, source of S, the variation of entropy of the reservoir. Then another question one can ask is what is delta Q from the system to the reservoir. Now, in your intuition, which is the sign of this delta Q? Is it positive or is it negative? Consider that the system is kept at T constant. So if you have this box here, with here there is the piston, and I move here, I am basically changing, well, converting the potential energy of the piston into heat. And this heat must be removed from the system in order to keep the temperature constant. So therefore, this heat must be negative in the sense that the system is providing heat to the thermal reservoir. Yeah, so for instance, how to find this dq, which is exchanged by the system to the reservoir. Well, this basically is just the variation of the volume of the system 2 times P0. So delta Q is just P0 times V2 minus V. And of course, this is negative because V2 is smaller than V. And by using the formula that we had before, this is just P0 V times X minus X squared plus 1, which of course is negative. Once we have dq, we can compute, for instance, the variation of the entropy of the source, because delta S of the thermal reservoir is just delta Q. Let me put a modulus here, because for delta S, this heat is positive because it is receiving this heat divided by the temperature, which is again constant. So for this, the variation of the entropy of the reservoir, which is equal to, let me write this, is P0V times X squared plus 1 minus X divided by temperature. This is the delta S of the thermal reservoir. Now we have to find the delta S associated with the subsystems 1 and 2. And I'm doing that just to remind you that once we know the initial state and the final state, the calculation of the variation of entropy basically can be done by following quasi-static transformation. Namely, the system like it is and the evolution of the system, of course, is a very violent evolution. So I cannot assume that when doing this rotation, the system will follow a quasi-static evolution, because it is a very, let's say, it's a quench, it's a very fast process. But I know the initial state, I know the final state, and since the entropy is a state variable, I can compute the variation of the entropy by following a path, which is a line, a normal line in the PV diagram, just being sure that the final state and the initial state are the same. Okay, the variation of entropy can be computed in this way. I do not need to describe the non-equilibrium states that are that the system will evolve into during this rotation. Okay, therefore one can do the following. System 1 has the following evolution: P and V. This is the initial state, and then will evolve into a state. Sorry, this is system 1 or system 2. Let me see. System 1 will expand, so then actually, yeah, so this is P1, this is V1. And I suppose that this is isothermal. Okay, just by, for the sake of simplicity, I can select another path if I want, but the easiest one now is isothermal, because also the T is constant. Although one has to specify, one has to take care of the fact that actually the system is not evolving through quasi-static evolution. Okay. So this is the situation for gas 1, and similarly for gas 2 will be something like that. So again, an isothermal, and then here I have a PV, and here I have P2, V2, because the volume is decreasing in the second case. Now we can compute the variation of the entropy along one isothermal, and this along this is easy because there is no variation of internal energy, right? So ds, so okay, first principle of thermodynamics, TdS is equal to PdV plus du. But this du is equal to 0 for isothermal and for ideal gas. Therefore, TdS is just PdV. I can use the ideal law gas again. So TdS is equal to P dV. And now I can write here T. What is P is kb, kb and T divided by volume. Then there is 1 over T, and there is dV. Therefore, you see that ds is just, I can remove this temperature here, is just kbn. Let me check if I got it correct. PB. L'ho lasciato così in termini di NKBT. Okay, sorry. Maybe it's better to work with pressure. Sorry. Or no, okay, I can do like that. Yeah, NKBT, and I can remove this. Okay, so this is NKB, and here I will have the log. This is in general of B final divided by B initial. So this is the variation of entropy along isothermal. Okay. Now, in the specific case of the system, I can compute this quantity for 1 and for 2, and then I get the following result. You can try to work it out. Delta S1 plus delta S2 is equal to PV divided by T, and I just write the final result because I have to do the log of V2 divided by V plus the log of V1 divided by V, and V1 and V2 were expressed before by the previous relations. So then I get finally the following expression: PV divided by T, then I have a log of 2x times x squared plus 1 minus x. Now, the tricky part here is that if you try to understand which is the sign of this, you will realize that this is negative. But this is not, let's say, something that can, it's not a violation of the second principle of thermodynamics, of course, because the system is not isolated, it is in contact with a thermal reservoir. And indeed, once you add delta S1, delta S2, and delta S of the source that we, of the thermal reservoir that we found before, you will get the following expression that is actually positive, as it should be. Espressione un po' lunga, ma ve la scrivo tanto per così. You will get this. So P0B divided by T, x squared plus 1 minus x plus PB divided by T. And here we have the log of 2x times x squared plus 1 minus x. Okay, where x was the ratio between P and P0. Okay. Okay. So what that, well, this was to say that, of course, the fact that this is negative is not a problem, okay, because the system is not isolated. Of course, the important thing is that the total variation of entropy is positive, and if you try to do the math here, well, actually, I don't think it can be done analytically, but you can show that this is positive. Well, as a function of x, by plotting this quantity as a function of x. Okay, x, of course, is a positive number. I think that today is enough for what concerns the exercise. Maybe I will do another one at the end if we have time. Now, what time is it now? Is 12. And maybe following the suggestion of the lady, we continue and we stop before. What do you prefer? Or we stop at some point? And what do you prefer? You can also express your. Maybe we can continue like 10 minutes more because we started later, and then we stop for a few minutes if it is okay for you.
Continuiamo, cioè, se non possiamo fare pausa, fino alla fine.
As you prefer. But usually I know from my experience that if I do like that, I arrive at 1 sharp. So it's better if I stop for a while. Otherwise, I will continue, most probably. Anyway, let me continue just 5 minutes and then we stop. I think maybe it's better. I know we are stuck here, but for people who are at home, of course, they can have a coffee. Now, after that, I think nobody will come back next time. If you have to get stuck here, maybe it's not so nice. Okay, so these were two exercises just to get familiar with to get familiar again with thermodynamics. Now let's move on and let us introduce what this guy here. Now let us consider the possibility of variation of number of particles. So let us remove the constraint that the total number of particles is conserved, and so we have the possibility to change the condition of my system, not only by changing the temperature, changing the volume, but also the number of particles. Now, to do that, one introduced a quantity which is called chemical potential, and in particular, the chemical potential is defined as follows. So basically, we start from the internal energy, the U, and the internal energy was written as TdS minus PdV. This is just the first law of thermodynamics. Now what we do is to add a term here, which is plus mu dN, where N is the total number of particles, whereas mu is the chemical potential. What is the interpretation at this level of the chemical potential, where is the variation of internal energy once as a response to a variation of number of particles, a fixed entropy and fixed volume. Okay, so this is just, if you want, the definition of chemical potential that we will find later on for ideal gas, for Fermi gas, and for Bose gas, which it's going to be a very important quantity actually. Now I will show a couple of things. First of all, I will show, I will prove a relation of thermodynamics, which is called the Gibbs Dwm Equation, which is the following. U, so not the differential, but U minus PS plus PB is equal to mu n. This is called the Gibbs Dwm Equation. Which will be useful in a moment, but let's try to derive first of all this equation. Now actually from this, one see that it was du is equal to ds minus pdv plus mu dn. U is a function of there's a t we are missing, entropy, volume, and number of particles. Okay, from this. Let me remove it now. And also let me remove this result here.
Scusi,
Sì.
anche dell'entropia ha detto, quindi bisogna aggiungere uno su.
Okay, I write it back again. D1 is equal to TdS minus PdV plus mu dn. And therefore, the internal energy is a function of entropy, volume, and number of particles. Okay. Now, those three variables are extensive. Well, actually, also the internal energy. U, S, V, N are extensive variables. What does it mean that they are extensive? Well, it means that they scale as the number of particles. So if I switch from n to alpha n, I get the same additional factor also to u, s, and v. So u will move into alpha u, v will move into alpha v, and s will move into alpha s. Therefore, I can write that the following equation, that u of alpha s, alpha v, and alpha n must be equal to alpha u, because of the fact that this is extensive. Okay, so if I compute u at this additional factor, multiplicative factor, which is multiplying entropy, volume, and particles, because they are scaling linearly with the number of particles, I must get that this is a function. So this function here must be alpha u, because this is also extensive. Okay. Now the trick is the following: is to take this equation. Let us call it asterisk, and make a derivative of this equation with respect to alpha. So derive alpha as a partial derivative. So what I get is the u is u, of course. When I derive by alpha here, I just get u. This is the partial derivative of u with respect to alpha s at fixed v and n times derivative of s alpha s with respect to alpha. I'm adopting the chain rule for computing the derivatives. Now, similarly for the other terms, so derivative of u with respect to alpha v at fixed entropy and number of particles times the derivative of alpha v with respect to alpha. And I just have the last term, which is the derivative of u, sorry, no, it's okay, u with respect to alpha n. Now this is a fixed entropy and volume, d of alpha n, d alpha. Okay? Now I can work out the derivatives here. This is just s, this is just b, and it's just n. And then we can put alpha equal to 1. And remember which are the Maxwell relations for u. The u with respect to s at fixed volume and number of particles is minus the temperature, is the temperature. The u divided by the v at fixed entropy and number of particles is minus the pressure. And the u with respect to n at fixed entropy and volume is just the chemical potential. Okay, so therefore in this equation I get the result, because now I can I have s times this guy here, which is ts. So this term becomes ts. This term here becomes minus pb. Minus pb. And the last term becomes plus mu n. Plus mu n. Okay. Now this relation is a fundamental relation of thermodynamics. Okay, because it connects all the quantities basically which are okay. So this is a very important and general formula. Now, this will be useful later on, so let's keep it there. Let me do another little calculation, and then we can stop. Questo l'abbiamo fatto. Now we can, well, maybe there are other ways to do it, but I'm done it in the following way. Let me use the fact that u is equal to dt ds minus pdv plus mu dn. And let me do the differentiate to differentiate this quantity here. So take a du, so take the differential of 1. So I get du is equal to TdS plus SDT minus BDP plus minus PdV plus d mu n plus mu dn. I think I have everything there now. Meno du, yeah. Okay. Let's call it, this is 1, let me call it 2, this equation here, and let me call this equation here 3. Now we can put 2 equal to 3, and remove all the terms that are in common. So TdS, PdV, UDN, TdS, UDN will cancel, and minus PdV. Therefore, I will get that VdP is equal to n d mu plus plus SDT. Okay, so this is just by using equation 2 and equation 3, I put 2 equal to 3, TdS minus PdV plus UDN will cancel, and then I just get, I have left only this term here, and SDT, yeah, in this term. Now let's take this equation here. From which I can get that dP is equal to n d mu plus s dt, where n is the density of particles, n divided by volume, and the small s is the entropy density, is the ratio between the entropy and the volume. Okay. Now this equation is interesting because it's an equation between the only intensive variables, because it's an equation between pressure, density, chemical potential, entropy density, and temperature. And from this equation I get 2 other Maxwell relations, which are the following. Those are 2 other useful equations when doing thermodynamics. The derivative of pressure with respect to nu at fixed temperature is equal to the density of particles. And the other one is that the derivative of pressure with respect to temperature at fixed chemical potential is the entropy density. Okay, so those are 2 other Maxwell relations. Maxwell relations. Those 2 relations are in presence of chemical potential. Therefore, they are useful when considering systems characterized by chemical potential and temperature. And those 2 relations are relations just among intensive variables. All intensive variables. In which context are those relations useful? When considering, let's say, infinite matter. In the sense that you consider a system without taking care of the volume, not even the surface, because we neglect always the surface, but also the volume. And so this is a situation in which you have, let's say, infinite matter, can be for for instance, those relations are very useful when modeling, for instance, matter in astrophysics. Okay, so typically for describing, I don't know, the sun or stars, the matter in those systems, one uses this quantity, this intensive quantity, and then add the gravity on top of that, and gravity will provide you the final volume actually. Okay, but the relations between the thermodynamical variables are relations provided by the microphysics. Okay, whereas the volume is provided by gravity. And in those situations, some of you has done already some astrophysics. It is very common to work with those Maxwell relations. So I would say that we stop for a moment, although it's 12 and 20, so I don't know what to do. Ci fermiamo qualche minuto o 2 minuti, just to, we can maybe move close to the window to put out the mask just for a moment. Okay, so let's stop for a couple of minutes, and then we continue with this. Another mic. Devo mettere a respirare. Do you think I can open the window? Le posso aprire la finestra? Un tappino questa. Ancora non ho parlato di quello che ne mandava.
Ah, no, non mi preoccupo. Anche perché penso che sia una cosa che già esiste.
Faranno quest'anno, forse no, l'anno prossimo dovrebbe esserci un corso di gruppo, diciamo, si chiama Meccanica Quantistica Advanced Quantum Mechanics, Moretti, credo che farà dei gruppi. C'è una cosa tematica.
Adesso per qualcosa la vedremo in campi. Adesso succede nei campi che adesso stiamo facendo. Però...
Ho guardato qualche libro di tutti, insomma.
No, perché poi io c'era la mattina che mi sono concentrato su altro, è una cosa che mi sono messo a fare un paio di giorni, però poi non ho fatto, quindi...
Ok, dai, riprendiamo. Dove che sta il corso? Okay, so let's make use of this Gibbs Dwm Equation. Now, okay, let me write it back again. It was the following. It was U is equal to T S minus P minus PB plus mu N. Then we know that A was so the Helmholtz free energy is the following quantity, whereas Gibbs is A plus PB. The Gibbs free energy was A, Helmholtz free energy plus PB, equal to U minus PS, which is the Helmholtz free energy plus PB. And now, by using the previous equation, U minus TS plus PB just mu N. Therefore, I conclude that the Gibbs potential is equal to mu N. Okay. In general, if I have a multi-component systems, because this is interesting when doing, for instance, chemistry or well, many other applications, in case of multi-component systems, which means systems with different species of particles or systems with different phases of the same particles. Now we will come back in a moment on that, so in the case of phase transition. So in that case, G can be generalized to be the sum over I of mu I and I, where this I, this index, refers to the species of the different particles. Okay. Now dg, so this is, if you want, the integral form of the Gibbs potential. When differentiating the differential potential, the Gibbs potential, we wrote last time, it's useful to have it in mind, that dg, it was equal to VdP minus SdT, and now I have to add plus mu Dn if I consider the possibility of changing particles, from which you see that dg with respect to N at fixed pressure and fixed temperature is equal to the chemical potential. Okay? And this is going to be important in a moment. This is the total variation of Gibbs potential, and this is the partial derivative of the Gibbs potential with respect to the number of particles at fixed pressure and temperature, and this is equal to the chemical potential. Now let's see a system in which we have, as usual, the two boxes, but this time with the same pressure, the same temperature, but different number of particles. And let's see what happens. Well, what thermodynamics, the second principle of thermodynamics describes. So we have now the usual box. Is a wall. On this side, we have a gas with pressure P, temperature T, and number of particles N1, and in principle V1, which is the volume, although it is not important. In this case, PT, N2, and V2. Of course, one has to specify, in this case, for the ideal gas case, V2 and V1 and V2, because if pressure and temperature are equal, and if the number of particles are different, then also the volume must be different. Otherwise, I get in trouble, no? Because PD for the ideal gas is KB and T. So if pressure is the same, temperature is the same, and the number of particles is different, so also the volume must be different. Otherwise, they will have the same number of particles. Now, what happens? Now this time, I have a system at fixed T, which again means a thermal reservoir, and fixed pressure, which is, let's say, the analogous of a thermal reservoir in the sense it's a constant pressure system. So you can think about having something acting on this box with a constant pressure. Well, in the typical case of the piston, could be that just that we have a weight over the piston, and that the pressure will be kept constant. Now, since P and T are constant, the second principle of thermodynamics tells me that one has to minimize the total Gibbs free energy, as was shown in the last lecture. Now, when we remove the wall, and let's compute, so when we remove the wall, and let us compute which is the variation of the Gibbs free energy. This is dG1 plus dG2, and this is equal to the derivative of G1 with respect to what? With respect to N1, because G is a function of pressure, temperature, and number of particles, as we wrote before. And therefore, I have to do this partial derivative at constant pressure and temperature, and variation of delta N1 plus dG2 divided by dN2, pressure, temperature, dN2. Okay. Again, the total number of particles must be conserved, as in the case, two other previous cases, we were conserving the volume and what we were conserving internal energy in the other cases. So dN1 plus dN2 is equal to 0, and this partial derivative are the chemical potentials. Okay, so then these equations has the following form. Delta G is equal to, this is mu1 delta n1 plus mu2 delta n2, but delta n1 and delta n2 are not independent. One is the opposite of the other one, and therefore I get mu1, for instance, mu1 minus mu2 times delta n1. Okay, so we know that delta G must evolve in such a way to be minimized. Okay, we have to minimize the free energy, the Gibbs free energy. This is second law. Therefore, if delta n1 is positive, then it must be that mu1 is smaller than mu2 in order to have this, right? mu1 smaller than mu2. Okay. So the second principle of thermodynamics in this system, which is a fixed pressure and fixed temperature system, tells me that the number of particles, well, the system will evolve in such a way that the number of particles of one increases if the chemical potential of one is smaller than the chemical potential of two, which means that we will have a flow of particles from 2 to 1, so from the high chemical potential region to the small chemical potential region. So this is the second law. Once we have equilibrium, delta G is equal to 0 at equilibrium, and this means that mu1 is equal to mu2. Once we have the equality of the two chemical potentials, we have reached the thermodynamical equilibrium, which in particular in this case is a chemical equilibrium. Chemical equilibrium. Okay. Now this relation, of course, is at the basis of chemistry. Because once you have different components in your system, and this is typically the situation in chemistry, there will be processes like diffusion, for instance, that will try to make matter flow from the high chemical potential region to the small chemical potential region. Okay, in order at the end to fulfill the constraint that the chemical potentials must be equal. Okay. So, and I think this closes the part of thermodynamics related to the second principle, which now was explained in several forms. And okay, I have some exercises more, but I will jump this. And let me move to the other topic, which is the last topic. Which is the last topic of the part of thermodynamics. Which is related to the phase-to-phase transitions, and in particular to first-order phase transition. This is going to be a phenomenological description of first order phase transitions. Phenomenological, if you want, thermodynamical descriptions of first order phase transition. At the end of the course, we will have a more microscopic descriptions of these processes once we have done a little bit of statistical mechanics. But it is useful to introduce the phenomenological description of phase transition just to get used to some names, some results, and in any case, it's very interesting physics by itself. So what I'm doing here is to introduce what is called phase diagram. This is not, let's say, just textbook physics, because dealing with phase diagram is one of the most active area, for instance, in nuclear and particle physics, or also in cosmology, because, for instance, having a sketch of the phase diagram of strongly interacting matter is one of the main, the most challenging problem in particle physics. Okay, so knowing for which conditions we have nuclear matter or quark matter or other kind of matter is one of the most important topic in nuclear and particle physics. Now, let's start from the beginning, well, from the most simple, well, it's actually not very simple, but the most common phase diagram, which is the one of water. And let's make a draw and describe qualitatively what's going on. So for the case of water, we have the following phase diagram. Can be drawn in different planes, but let's start with the PT plane. That is the following. Now, let me write what are the names of those phases. Okay, so what's going on here? We have water. We are familiar with three phases of water: ice, water, and vapor. This liquid, this solid, and this gas. Now, intuitive descriptions of those phases is the following. Ice has so the solid has a crystalline structure, therefore is a ordered structure in which the shape of the body will be independent from anything. It could just be the way it is without any external agent. Water, in presence of gravity, takes the shape of the volume in which it is. In empty space will be just a sphere in order to minimize the surface effects. Whereas vapor will try to have to occupy all the volume which is at its disposal. Okay, so this is basically a phenomenological description. We have a crystalline structure here, and in those cases we have not crystals, so we have more disordered matter. And the difference between water and vapor are that the fact that in this case it will expand, whereas water will not, just occupy a certain volume with the shape of the box in which it is. Now, what are these lines? You see that there are solid lines and dashed line, and one dashed line, and there are 2 points. One of them is called critical point, which is this, and the other one is a tripole point. The tripole point is the point of pressure. Well, it determines the pressure and the temperature at which these 3 phases can coexist. Okay? The tripole point means that those 3 phases in coexistence. The critical point, basically, we will analyze this more deeply later. Basically, it's a point after that, after which you cannot distinguish anymore what is water and what is vapor. Before coming to that, indeed, it is better to talk about what are the first, what are the continuous, the meaning of the continuous line. The continuous line, as you see, separates the phases, and they are called continuous line. They are corresponding to first order lines, first order phase transition. What they do is to separate the phases, the different phases. So this line here separates ice from water, and this line here is ice from vapor, and this line vapor from water. But at some point it ends. It's a critical end point, which is called critical point. And after that, so if you are sitting here, basically the difference between water and vapor is not very evident. Okay, they are basically the same. And here, the critical point, something very interesting happens that we will see at the end of the course. Now, let's try to specify a little bit more what's going to happen when crossing those lines. Suppose that I draw an isothermal line there, crossing the solid lines as follows. Okay, so this is a certain temperature T star. Now, in this diagram, I see that the same temperature, by just varying the pressure, correspond to different phases. Here we have vapor, ice, and water. Now, if along this T star line I draw an isothermal, because this is an isothermal, but I move in the PV plane, how does the line, how does the PV plane, the line of the PV plane look like? It will be something like that. Okay, first of all, what is the isothermal for ideal gas? For ideal gas, the isothermal PV will be something like that, no? T constant. In which the pressure is just temperature divided by volume. Okay, so it's 1 over V. Now, in real systems in which you can have phase transitions, so different phases of the same kind of matter, the situation is much more complicated than this one. And actually, by taking into account the phase diagram, what we'll have is something like that. So for large temperature, so let me make here some So for small pressure, we just have vapor here, and we are here. Then here we will have ice, and at the end, for very large pressure, sorry, we will have water. Notice that the specific slope of this line is not trivial. This is done like that just for water. For other kind of matter, is not the same. Okay, that the slope of this line indicates that if you have ice and you compress this ice at fixed temperature, at some point you go to the liquid phase. Okay, which is the peculiar feature of water, and that is the reason for which you can ski, no? For instance, okay? There are many phenomena related to the fact that if you press ice, you get water. Okay? Now, so you have these branches corresponding to vapor, ice, and water, and what happens here is that you have plateau. Those two plateaux of the pressure, that corresponds to mixed phase. So these regions actually are occupied by mixed phases. And in particular here, 1 and 2, in 1 you have a mixed phase of vapor and ice, whereas in 2 you will have a mixed phase between ice and water. Okay, and these two plateaux, of course, correspond to these values of pressure. Let's call it P1 and this P2. This P1 and this P2. Okay. Let me see if I have to tell you more about that. Yeah, this is the. Now let's move a little bit and let's go here to the temperature corresponding to the tripole point. Let's call it TT, just for the tripole point. The situation will be similar to that, but still very far away from the ideal gas case. And in particular, for the temperature corresponding to the tripole point, so we'll have a diagram like that, beginning with a plateau. Here T was T star. And we have a mixed phase, one mixed phase with 3 components. Okay, this is the situation corresponding to the tripole point in the PV plane. And now let's draw also the isothermal line corresponding to the critical point. So let's draw here a line corresponding to T equal to TC, where C stems from critical. Let me maybe remove this. Now, in this case, the isothermal has the following shape: P and V, and this is temperature equal to critical temperature. We will have something like that. A point in which the derivative of the pressure with respect to volume is 0. This is the critical equation. Okay. And as I said before, when we have above the critical temperature, so above this temperature, basically there is no distinction between water, and vapor. They are basically almost indistinguishable. Okay, there is no separation of phases. Whereas in the mixed phase case, you really see a mixed phase in the sense that there are blocks of ice in water, or you can have bubbles of vapor in water. Those are the mixed phase you already are familiar with. Now, where you boil water, there is a certain stage in which you will have water and bubbles of air, of vapor inside, which coexist exactly at T equal 100 Celsius and 1 atmosphere of pressure. Okay, and similarly for ice and water. Okay, those are mixed phases. Now you can distinguish the two phases. Now, what time is it? 54. Let me just make this introduce this other term. So just to make an example on how this phase transition work. Okay, you have the case already of melting of ice. You have the case of boiling of water. Those are first order phase transitions. Okay. If you take, for instance, let's concentrate for a moment on the liquid gas phase transition. Critical point, focal point, and suppose that we have a system at a certain temperature T star. Now, suppose that you take a liquid and put this liquid in an empty box. Empty means without any particles, okay? At a certain temperature T equal to T star. Is at the beginning is completely empty, and now you put a certain amount of liquid. What will happen is that basically the system will evolve in such a way to have a separation of phases. That means that some particles from the liquid will evaporate, until at some point you reach a situation in which you have again a T star. We are working at the same fixed temperature. You have a liquid, and here it's gas or it's vapor at equilibrium. And this happens exactly at this point here. Okay, so when the isothermal curve crosses the first order transition line separating the liquid and the gas, this pressure P is called vapor pressure. So this vapor pressure is the pressure that is reached when liquid and vapor are at equilibrium. Liquid and vapor at equilibrium. By equilibrium here I mean thermodynamical equilibrium, which basically means that there is no change of temperature, no change of volume, everything is stationary. Okay. Now, a gas which is at the pressure which corresponds to the vapor pressure is a gas in saturation. It's called. Okay, you might know this. Now, of course, so we are in this situation. Basically, we are sitting here in which we have a separation of phases. Vapor and liquid, they coexist at the same temperature and the pressure, which is called the vapor pressure. Now, if you introduce a piston here in the side in which you have the vapor, you can move along this line. If you put this box in contact with the thermal reservoir, and by changing the pressure acting on the piston, you can basically move towards the water case, the liquid case, if you increase the pressure, or if you decrease the pressure, you can move towards this other phase, no? And so you can change, if you are here, you can change the composition of the mixed phase, which means the number of particles that are in the liquid phase and the number of particles which are in the vapor phase, by just changing the pressure. But the pressure will not change actually because of the plateau. Okay, we will see this next time. And I think now it's 1 and it's better to close. Anyway, something about first order phase transition is familiar to you from general physics course or not at all, or from chemistry maybe from chemistry. Okay, in any case, it's better to do it because it's something important. Okay, see you on Thursday.
Arrivederci.
Vabbè.